When you send a message to someone on the other side of the world, where does it actually go? Through the air? Through a satellite? Through the cloud? Not really. Most of the world's international data does not travel through space. It travels through the ocean, beneath the waves, across the dark floor of the Atlantic, the Pacific, and the Indian Ocean. There is a hidden network of fiber optic cables connecting continents together. They are thinner than you imagine, more important than most people realize, and far more vulnerable than the modern world wants to admit. Every video call, every bank transfer, every stock trade, every message crossing an ocean may pass through a glass thread, buried in darkness beneath thousands of meters of water. And if those threads are cut, entire countries can slow down, businesses can freeze, and governments can panic. This is the story of the invisible network that holds the internet together. The ships that build it, the weak points that threaten it, and the silent geopolitical struggle happening beneath the sea. The map of the internet is not a cloud. It is a map of physical routes, cables, landing stations, data centers, and exchange points. And the most important routes are underwater. Around 99% of intercontinental digital traffic travels through submarine fiber optic cables. Not because satellites are useless, but because cables are faster, cheaper, and can carry far more information. A satellite signal has to travel up into space and back down again. That distance creates delay. For some uses, that delay is acceptable. But for financial trading, live video calls, online gaming, cloud computing, and military communication, milliseconds matter. So, when someone in New York video calls someone in London, their voice is converted into digital information, then into pulses of light, then sent racing through a fiber optic cable lying on the floor of the Atlantic Ocean. The journey can take less time than it takes to blink. A submarine cable looks simple from the outside, just a thick black line. But inside, it is an engineering miracle. At the core are strands of glass, sometimes thinner than a human hair. Data travels through those strands as pulses of laser light. Around that fragile glass core are layers of protection, plastic insulation, copper, steel wires, water-blocking material, and a tough outer jacket designed to survive pressure, salt water, abrasion, and decades of use. In the deep ocean, where there are fewer anchors and fishing nets, the cable can be surprisingly thin, sometimes not much thicker than a garden hose. Near the shore, where danger is greater, the cable becomes much heavier and more armored. Some of these cables carry astonishing amounts of information. The M-Area cable, connecting the United States and Spain, was designed with a capacity of more than 200 terabits per second. That is enough to support millions of high-definition video streams at the same time. And yet, all of that global traffic passes through physical objects that can be damaged by an anchor, a landslide, an earthquake, or a ship dragging equipment across the seafloor. The internet feels weightless, but it has a body, and that body lies under the sea. To build this hidden network, humans use some of the most specialized ships on Earth. Cable-laying ships are not ordinary cargo vessels. They are floating factories, repair workshops, and navigation platforms built for one purpose: to place thousands of kilometers of cable across the ocean floor with extreme precision. Before a cable is laid, survey ships map the route. They study the seabed, looking for underwater mountains, trenches, fault lines, coral reefs, unstable slopes, and areas where fishing or anchoring could become dangerous. The goal is to find the safest possible path across a landscape most people will never see. Once the route is chosen, the cable ship begins its slow journey. The ship moves at roughly walking speed. The cable is fed carefully from massive circular tanks, guided through machinery, and lowered into the ocean behind the vessel. In deep water, the cable is usually laid directly on the seafloor. But near coastlines, where ships drop anchors and fishing gear scrapes the bottom, the cable is often buried. A remote-controlled underwater plow digs a trench, places the cable inside, and covers it again. This is one of the strangest parts of the modern internet. Before your data can cross the world at the speed of light, someone has to slowly drag a cable through mud under the ocean. Laying a major transoceanic cable can take weeks or months. It can cost hundreds of millions of dollars, and the work has to be almost perfectly coordinated. The cable cannot be stretched too tightly. It cannot be dropped too loosely. It has to follow the mapped route, and every kilometer matters. When the cable finally reaches land, it does not simply appear on a beach and plug into the internet. It enters one of the most important buildings in the global communication system. The places where submarine cables reach land are called cable landing stations. From the outside, they may look boring. Plain buildings, fences, security cameras, sometimes hidden near quiet coastal towns. But inside, they are choke points of the digital world. This is where the undersea cable connects to terrestrial fiber networks. From there, the data moves inland toward data centers, internet exchange points, telecom networks, banks, cloud platforms, and eventually your phone. A landing station is not just a technical building. It is a strategic asset. If a country has many cable landing points, it has resilience. If it has only a few, it has vulnerability. And this is where the story stops being only about engineering. It becomes about power. Submarine cables are strong, but they are not invincible. Most cable faults are caused by ordinary human activity. Fishing gear, ship anchors, dredging, and accidents near busy coastlines. Sometimes, the damage comes from nature. Earthquakes and underwater landslides can break several cables at once, cutting off or slowing communication across large regions. And yes, sharks have bitten submarine cables. That detail became famous because it sounds almost unbelievable. The internet, attacked by sharks. Scientists have debated why sharks sometimes bite cables. One theory is that they may detect electromagnetic fields and mistake the cable for something alive. Cable companies have responded by using stronger protective materials, especially in vulnerable areas. But today, sharks are not the main threat. The bigger danger is much less exotic and much more human. In 2008, a series of submarine cable cuts near Egypt and the Persian Gulf disrupted internet access across parts of the Middle East, North Africa, and South Asia. The incident was a warning. A few damaged cables could slow down entire regions. Businesses suffered. Call centers went offline. Internet traffic had to be rerouted across longer paths. The world learned that the internet has bottlenecks, and those bottlenecks can break. Then there is the darker possibility. Sabotage. In recent years, governments and military analysts have become increasingly worried about the security of undersea infrastructure. Submarine cables are difficult to protect because they are long, remote, and often pass through international waters. A cable may stretch for thousands of kilometers, but only a few sections need to be damaged to create disruption. You do not always need a submarine. A ship, an anchor, or specialized underwater equipment could be enough. And in a crisis, the consequences could be enormous. Financial systems depend on these cables. Cloud services depend on them. Military communication depends on them. Global news, logistics, trade, and banking all depend on them. The modern economy runs on light, moving through glass under the ocean. That makes submarine cables both beautiful and terrifying. They are the veins of globalization, and every vein is a target. But the idea of connecting continents under the sea is older than the internet. In 1858, the first transatlantic telegraph cable connected Ireland and Newfoundland. It was a copper wire insulated with gutta percha, a natural material from tropical trees. That first cable failed after only a short time, but it proved something revolutionary. Continents could be connected almost instantly. Before the cable, a message from London to New York had to travel by ship. It could take more than a week. After submarine telegraphy became reliable, messages could cross the Atlantic in minutes. The world began to synchronize. Markets, diplomacy, newspapers, empires, and families all moved faster because of a wire under the sea. The internet did not invent the connected world. It inherited it. Today, a new generation of cables is being built. In the past, many cables were funded mainly by telecom companies and international consortia. Now, some of the biggest investors are technology giants. Companies like Google, Meta, Microsoft, and Amazon, because their cloud platforms and data centers need private, high-capacity routes around the planet. New routes are also being explored in the Arctic, where shorter paths between Europe, Asia, and North America could reduce latency. Projects such as Polar Connect and Far North Fiber show how important these northern routes may become. But the Arctic is not an easy shortcut. It is remote, icy, politically sensitive, and extremely difficult to repair if something goes wrong. The future of the internet is not just about more speed. It is about resilience, more routes, more redundancy, better monitoring, faster repairs, and a network that can survive accidents, disasters, and conflict. Because a fragile internet is not just a technical problem, it is a global risk. So the next time you send a message across the world, remember where it really goes. Not into a magical cloud, not simply through the air, but through a glass thread, thinner than a hair, protected by steel, hidden beneath the crushing darkness of the ocean. It may pass over mountains, under the sea, across earthquake zones, near fishing grounds, past silent submarines, through landing stations most people will never notice, and somehow it arrives in another person's pocket in less than a second. The internet is not magic. It is engineering, it is geography, it is history, and it is one of the most fragile systems holding the modern world together. If you love uncovering the invisible systems that make everyday life work, subscribe for more stories about the maps, machines, and hidden networks behind our world. And tell us in the comments, what piece of infrastructure should we explain next?